Let's have a look. So remembering anti-differentiation is a way of going from the derivative back to the original function. So in terms of kinematics, if you think about it, we've got our position to our velocity to our acceleration, and to go from position to acceleration, it's differentiation. Now let's put dv dt there. Oh, let's change that to dx dt to dv dt. If I've got my acceleration and I want to go back to the velocity, or from my velocity and I want to go back to the position, I've got to do anti-differentiation. Okay, so this is where maybe confusion can get in the way. Okay, the key is, I think, derivatives are about a rate of change. So dx dt, change in x over change in time. And how quickly does your position change? Well, that's velocity. How quickly does your velocity change? That's acceleration. So if I want to go from acceleration back to velocity, I anti-diff. Velocity to position, I anti-diff. So let's have a look. A body starts from the origin and moves in a straight line. After t seconds, its velocity is given by that. Find its position. So velocity, which is dx dt, is equal to 2t minus 4. So that means then that x is equal to the antiderivative of 2t minus 4 with respect to t. Okay, so that's our notation we're going to use. So x is equal to 2t, add 1 to the power and divide by the power, minus 4t plus some constant c. So my position is actually t squared minus 4t plus c. Now, if I got the initial condition, a body starts from 0 and moves in a straight line. It starts from 0, so we can, I reckon, read from that. At t equal to 0, the velocity is equal to 0. So if I put that in, and the position, and also position is equal to 0. So because we're starting from the origin, so if I do that, substitute that in, it's only going to give me c equal to 0. So there's my rule for the position. Oh, we don't need the c though. X equals t squared minus 4t. Find its position after 3 seconds. Well, x is equal to t squared minus 4 times t, 9 minus 12, which is equal to negative 3 meters. What is this distance travelled in the first 3 seconds? So before we answer that, we really need to have an idea of what the motion looks like. I know after 3 seconds I'm 3 meters away, so I started at the start. You could argue that all we've travelled is 3 meters, but let's have a look at the graph of it. So there's x, there's t, and the graph is t squared minus 4t. So what does that look like? I've got, it factors to t minus 4. It's a positive parabola, so it looks like that. Yeah. So what does that mean? As a graph, it simply means that we were heading away. We were heading away from the origin to the left for the first, what? 2 seconds, isn't it? Because it's a parabola, so it's symmetrical. Then after 2 seconds, the gradient is 0, which means my velocity is 0. We stop and turn around, and we head back in a positive direction. So how far have we travelled? So at t equal to 2, where are we? So at t equal to 2, x is equal to 4. I shouldn't put it like that. Let's put it like, I'm going to substitute it into the position equation, equal to 2 squared minus 4 times 2, which is 4 minus 8, which is negative 4 meters. So we're negative 4 meters, so we're 4 meters to the left of the starting point after 2 seconds. At 3 seconds, we're there, and that's, what's that? That's negative 3 meters. So if we think about it, the total distance traveled is the blue section of the line here, which is 4 meters, plus this green section of the line here, which went from negative 4 to negative 3, which was 1 meter. So the total distance we traveled was 5 meters, okay, in those first 3 seconds. Just like when we get back after 4 seconds, we're back at our starting point. So clearly we haven't traveled 0 meters in the first 4 seconds. My displacement is 0, but the distance I've traveled, I went 2 meters to the left, sorry, negative 4 meters to the left, so 4 meters to the left, and then I came back 4 meters to get to the starting point again. Average velocity in the first 3 seconds. All right, so average velocity. So as soon as they talk about average, we're no longer talking about the derivative. So it's the change in position over the change in time, which is, I guess, y2 minus y1 over x2 minus x1. So after 3 seconds, I was at negative 3 meters minus my starting position, which is 0. And the time it took me to get there was 3 seconds. So on average, my average velocity was negative 1 meter per second. All right. My average speed, on the other hand, all right, particle starts from rest 3 meters from a fixed point and moves in a straight line with an acceleration of, find the position and velocity. So acceleration is equal to dv dt, okay, which is equal to 6t plus 8. So to get from acceleration to velocity, I do an antiderivative. And that will give me add 1 to the power, divide by the power, plus 8 add a power. So the velocity is equal to 3t squared plus 8t plus some constant c. So we need some initial information here. Starts from rest, 3 meters. So at t equal to 0, my velocity is 0, isn't it? Starts from rest. So if I sub in, I get 0 is equal to 3 times 0 squared plus 8 times 0 plus c. So c is equal to 0. So I've got a rule for the velocity, 3t squared plus 8t. Now I need a rule for my position. So velocity, which is dx dt, therefore my position x is the antiderivative of my velocity. With respect to t, so x is equal to t, add 1 to the power and divide by the power, plus 8t, add 1 to the power, divide by the power, plus some constant. I'll put a d because I used c earlier. It doesn't matter, but we should use the same one. 3 on 3 is t cubed, plus 8 on 2 is 4, plus some d. So what initial conditions do I got here? Have I got here? 3 meters at t equal to 0. So at t equal to 0, my position x is equal to 3. Substitute that in. 3 is equal to 0 cubed plus 4 times 0 squared plus d. So d is equal to 3, and my position x is equal to t cubed plus 4t squared plus 3. So there's my position, velocity, and acceleration formulas. And then depending upon what, if I needed to work out a few other things, you know, when is a particle stationary, when is it at a furthest distance away, I work with those different rules. Okay, so example 23. A stone is projected vertically upwards from the top of a 20-metre high building with an initial velocity of 15 metres per second. All right, find all these different rules. So let's think about, because it's acting vertically up, what we do have is the acceleration is acting. My acceleration is negative 9.8 metres per second squared. That's what gravity is. Okay, so hopefully we've discussed that a little bit earlier. So my gravity is slowing my object down. So when we throw a ball, Newton discovered it from memory, threw an apple up, or the apple fell down and something made it fall down. It was gravity that made it fall. So gravity is going to slow the ball that we throw up in the air at 9.8 metres per second squared. So let's find out all our equations. So if that's acceleration, my velocity is the antiderivative of negative 9.8 with respect to time. So velocity is equal to negative 9.8t plus some constant c. And we projected vertically upwards, initial velocity of 15 metres per second. So at t equal to 0, v is equal to 15, and therefore, hopefully you can see that's what my c value will be. If I put t equal to 0, I'll get c equal to 15. So my velocity is equal to, I'll put negative 9.8t plus 15. Let's go to my position. Position x is equal to the antiderivative of my velocity with respect to time, which is equal to negative 9.8t to the power of 2 on 2 plus 15t plus some other constant, we'll call it d, negative 4.9t squared plus 15t plus d. So there's my position. And at t equal to 0, I actually am 20 metres in the air. I'm on top of the building. So at t equal to 0, my position is equal to 20. And again, if I put t equal to 0 in there, whoops, I'm going to get d equal to 20. So I've got a rule now for the position. Negative 4.9t squared plus 15t plus 20. So if I need to work with the position of my stone, there's one equation. If I need to work with the velocity of my stone, there's the other equation. Let's just rub out that line in front. That shouldn't be there. All right, so find the time taken for the stone to reach the maximum height. So when does the maximum height occur? If I throw a stone up in the air, it's going to reach its highest point when my velocity is 0. So let's solve. So let's, maybe in green, I'll sneak in about here. I need velocity equal to 0. So negative 9.8t plus 15 has to equal to 0. So t is going to equal 15 over 9.8. T is equal to, it works out to be 1.53 seconds. Okay, find the maximum height reached by the stone. In other words, where is the particle after 1.53 seconds? So I've got to substitute that into the position rule. So I'm going to put x is equal to negative 4.9 times 1.53 squared plus 15 times 1.53 plus 20, and that gives me 31.47 meters. Okay, what is the time taken for the stone to reach the ground? So in other words, I need x equal to 0. So I need to solve negative 4.9t squared plus 15t plus 20 equal to 0. We're going to use our CAS here. So solve on the calculator will give me t is equal to. So we can see there from our CAS, from our printout there that x is equal to negative 1 or x is equal to 4, so the t variable. So we can see there that our time, it will take 4.06, so 4.07 seconds to get back down to the ground. What is the velocity of the stone at that time? Well, if I put t equal to 4.07 into my velocity rule, negative 9.8 times 4.07 plus 15, again, we can see on the CAS that it will have a speed of negative 24.84 meters per second. So a speed of 24 meters per second heading downwards, that's what the negative sign suggests. All right, so I hope that makes sense. Off you go.